Almost 150 years before actual atomic theory was established, Boyle, Newton, Bernoulli and several other scientists tried to explain the behavior of gases. They considered that gases are made up of tiny atomic particles. Later in the 19th century, Maxwell, Boltzmann, and others successfully developed kinetic theory. Kinetic theory explains the behavior of gases based on the idea that gas consists of atoms or molecules which are in constant random motion. Kinetic theory has widespread applications. This theory leads to the molecular interpretation of pressure and temperature of a gas. It is also consistent with gas laws like Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's hypothesis. Kinetic theory helps explain the specific heat capacities of many monoatomic, diatomic, and polyatomic gases. It relates the measurable properties of gases like viscosity, conduction, diffusion to the size of molecules. In fact, these relationships help in the estimation of molecular sizes and masses. The atomic hypothesis is one of the most important theories ever proposed. What is the atomic hypothesis? According to the atomic hypothesis, all things are made up of tiny particles called atoms. These tiny particles move around in continuous or constant motion. Atoms attract each other when they are separated by small distances and repel each other when compressed into one another. Atomic theory is credited to John Dalton. Dalton's atomic theory states that all matter is composed of atoms. Atoms cannot be made or destroyed. All atoms of the same element are identical. Different elements have different types of atoms. Atoms of two or more elements combine to form chemical compounds. In fact, Dalton had proposed atomic theory to explain the law of definite proportions and the law of multiple proportions, which are obeyed by elements when they combine to form compounds. The law of definite proportions states a given compound always contains the same proportion of elements by mass. For example, consider a water molecule. The ratio of the mass of oxygen, MO, to the mass of hydrogen, MH, in a water molecule is always fixed and is independent of how the water molecule is formed. The law of multiple proportions states that when two elements are combined to form more than one compound, then, for a fixed mass of one element, the masses of the other elements in different compounds are in the ratio of small integers. For example, carbon and oxygen combine to form two compounds, carbon monoxide and carbon dioxide. If M1 is the mass of oxygen that combines with M units of carbon in the carbon monoxide, and M2 is the mass of oxygen that combines with M units of carbon in carbon dioxide, then, according to the law of multiple proportions, the ratio M1 is to M2 is a simple ratio of small integers. Dalton's atomic theory, when combined with Avogadro's law, helps explain Gay-Lussac's law. Gay-Lussac's law states that when two or more gases combine chemically to form another gas, then the ratio of volumes of the gases are in the ratio of small integers. And Avogadro's law states that at constant temperature and pressure, equal volumes of all gases contain the same number of molecules. An interesting thing to note here is that Dalton's atomic theory is also known as the molecular theory of matter, as the elements are often found in the form of molecules. Generally, the size of an atom is about an angstrom unit, which is equal to 10 raised to the power minus 10 m. In solids, the interatomic separation is very small, approximately 2 angstrom, whereas in liquids, the atoms are separated by 2 angstrom, but the atoms of liquids are less rigid than those of solids, and hence the liquid can flow. Whereas, in gases, the interatomic separation is very large, approximately 10 angstrom. In solids, the atoms are tightly packed. That is, the interatomic force is strong. In liquids, the atoms are loosely packed. That is, the interatomic force is weak. Whereas, in gases, atoms are very loosely packed. That is, the interatomic force is negligible. Due to interatomic forces, solids have a definite size, shape, and volume. Liquids have definite volume but no definite size and shape, and gases have neither fixed volume nor definite size and shape. The molecules and atoms of matter can be seen through electron microscopes and scanning tunneling microscopes. So we now know that atoms are divisible and are not elementary. An atom is made up of a nucleus in the center and electrons revolving in orbits around the nucleus. Protons and neutrons together make up the nucleus of an atom. These protons and neutrons are further made up of quarks. It is believed that quarks may be further made up of string-like elementary entities. In case of gases, interaction between molecules is negligible, except during a collision because the molecules are far away from each other. So, it is easier to study properties of gases such as pressure, temperature, and volume compared to that of solids and liquids. Gases at low pressure and high temperature satisfy a simple relation. PV is equal to kT, where P is the pressure, V is the volume, T is the temperature in Kelvin scale, and K is the proportionality constant. Let this be equation 1. For a given sample of gas, K is constant, and can be written as K is equal to N multiplied by Kb, where N is the number of molecules in the given sample. From observation during various experiments, it is clear that the value of Kb is constant for all gases and is called the Boltzmann constant. Its value is 1.38 into 10 raised to the power minus 23 joules per Kelvin. Substituting the value K is equal to NKB in equation 1, PV is equal to KT. We get PV is equal to NKBT. Let this be equation 2. We know that 1 mole of gas contains an Avogadro number of molecules denoted by Na. So, N is equal to N into Na, where N is the number of moles of the gas present. Substituting the equation N is equal to N into Na in equation 2, PV is equal to NKBT. We get PV is equal to N Na into KBT. Upon rewriting the terms of the equation, we get PV is equal to N into NaKB into T, which can be written as PV is equal to nRT. Let this be equation 3. In equation 3, R is equal to Na into Kb is called the universal gas constant. The value of R is 8.314 joules per mole per Kelvin. This value is constant for a given system of units. Equation 3 is also called the ideal gas equation. A gas that satisfies the ideal gas equation at all temperatures and pressures is defined as an ideal gas. The concept of an ideal gas is merely a theoretical concept. In practice, there is no ideal gas.